So let's do a two-dimensional kinematics review. So the first thing that you see here on the review sheet on our website, and if you're not sure where to get this document that I'm looking at, please go to our website, www.fizzixfun.com, click on assignments, and you'll see these 2D kinematics review notes. So everything you know about 1D kinematics can be applied to 2D. And in fact, we're not even doing anything new this unit that you haven't already seen before, aside from resolving vectors at an angle. So what I mean by that is all of the problems that we solved in 1D kinematics, such as a car accelerating on a road, or an object being thrown up in the air or released from rest, all of those same scenarios are happening right now in 2D kinematics. So the only difference between 2D and 1D is that we're simultaneously looking at the x direction and the y direction in the same problem. So we started our unit with a short conversation and reading in your book on projectile motion. Projectile motion is defined as free fall with a horizontal velocity. So you guys know when objects are in free fall, they are accelerating according to gravity. So in the y direction, we have an acceleration of negative 9.8 meters per second squared. And in the x direction, by definition, we have an acceleration of 0. If objects were to have an acceleration that was non-zero in the x direction, that would mean that while you're sitting in your chairs in class, you would be swaying left and right like little pieces of seaweed because you would be accelerating horizontally. So when you're sitting in class taking the test, remind yourself that you're accelerating downward because of gravity, and you're not accelerating left or right because there is no horizontal acceleration. Okay, so we started this unit with an activity on projectile motion utilizing video physics. So you guys took a video of projectile motion, someone throwing a ball in the shape of a parabola, and you plotted points and you created the y position, y velocity, and x position, x velocity graphs. So hopefully your graphs look something like this. Your y position graph actually took the shape of your object, and that's something to note. And then your velocity graph should have been linear in the y direction. Two things that were important from that activity is to note where you find important key points. So if you look here, y initial is the y coordinate of the first point on this graph, and y final is the coordinate of the last point on this graph. And so delta y you can determine from y final minus y initial. In the same way, the first y coordinate on your y velocity graph would tell you VIY, and the last y coordinate on your velocity graph would tell you VFY. And of course, the slope of this graph would tell you acceleration in the y direction. In the horizontal axes, the first coordinate on your x position graph would tell you x initial, and the last coordinate on your x position graph would tell you x final. And of course, the difference of these, x final minus x initial, would give you delta x. The slope of this graph would tell you the x velocity, and the first coordinate on this velocity graph would tell you VIX, and the last coordinate would tell you VFX. And you guys know, since acceleration in the x is 0, this velocity should be constant. In the projectile lab, when you do the line of best fit for the y position graph, which is quadratic, so that's this one here, graphical analysis pops up the table or the data box that shows you the equation for the line of best fit. So remember, the least useful thing an equation does is spit out a number, and the most useful thing it does is tell you a relationship. So when you're looking at the equation of your line of best fit, in graphical analysis, you'll notice that it resembles our quadratic equation that we have for delta y. What that means for us is that the coefficient a should be represented by 1/2 vertical acceleration, or 1/2 of 9.8. So everyone should have had the same capital A coefficient of about 4.9. And whether you made up positive or down positive would depend on whether that's negative. The coefficient b then corresponds to VIY, and so for each group that would be different because it would depend on how you threw the ball, how quickly you threw it. So it's really important to understand what the equation of the line of best fit tells us, and to see that the kinematic equations that we use in class are actually derived from graphical data. 3.1 in your book began talking about vectors, and vectors are just arrows. They are an arrow quantity that we use to represent any mathematical vector quantity. Recall that a vector quantity is a quantity that has both a magnitude, indicated by the length of the arrow or the size of it, and a direction, indicated by the direction of the arrowhead, whether that's down, to the right, up at an angle in quadrant 1, or vertical. If you were to draw the vectors of velocity on a projectile, like your book has, and like we've done here, you would see that the resultant vector vi, or the total velocity at any point, is actually the result of both the horizontal component of the velocity vx and the vertical component of the velocity vy. So at any point, total velocity v, indicated by the blue arrows, is the hypotenuse of the right triangle that's formed by the horizontal component vx and the vertical component vy. And here I've just moved the orange arrow over to the object rather than drawing it right here like I normally do. You'll also see in this vector diagram that we have acceleration a in the vertical axes of negative 9.8, and that acceleration is actually constant throughout the motion, even though you guys know that at the peak, at point C, Vy is 0. So just like in one-dimensional motion, velocity is 0 at the peak, but that is velocity in the y direction, not velocity in the x direction. Velocity in the x direction is constant. Velocity in the y direction changes. And here we say on the way up, Vy and A point opposite directions. Therefore, that's what these three dots are. Therefore, the object slows. That's nothing new. You guys have seen that in one-dimensional motion when you throw a ball up and catch it in the same place. On the way down, Vy and A point the same direction, and therefore the object speeds up. Something important to note is that in your WebAssign problems on your homework, when a problem asks for the final speed or the final velocity of an object, they're asking for this quantity here, Vf. When you use the kinematic equations to solve for Vfy here in orange, you're not actually finding the total final velocity, you're finding the vertical component of it. And so you still need to use Pythagorean theorem to find Vf. The equations that you'll get on the test are listed here, and I will actually give you our sine, cosine, and tangent equations. But you'll see that the y direction equations are the same as the ones that we had last unit. The x direction equation is actually the same as this one here, as the delta y equation. The only difference is that since ax is 0, this entire squared term here drops off when you're talking about the x direction. So we really only have one relevant equation for x, and that's delta x equals vxt. These equations here become less useful for us as our graphs are mostly quadratic, meaning curved, and so the velocity on the position graph is changing. We had a brief discussion about right triangle trigonometry, and please don't be intimidated by the word trig if you haven't taken the class, because all of you have seen this in geometry. So we said that for a right triangle, there are three sides, or three lengths: the hypotenuse, the opposite side, and the adjacent side. And yes, I know that this is spelled incorrectly. The sine of an angle is a function, and that can be calculated with the angle theta. So we say that this angle here, we're calling theta, that's the Greek letter theta, and when you take the sine of that angle, that quantity sine theta is equal to the ratio of the opposite side over the hypotenuse. There's another function we use called cosine theta. When you take the cosine of an angle theta, and again theta is just the variable that represents the unknown angle, that is equal to the ratio of the adjacent length, or the length of the adjacent side, divided by the hypotenuse. Just doing simple algebra, moving the hypotenuse over to one side and solving for the unknown length of the side opposite the angle, and solving for the unknown length of the side adjacent to the angle, we get these two equations. Opposite side equals hypotenuse times sine theta, and adjacent side equals hypotenuse times sine theta. Now, if we take this simple math and we apply it to the velocity vectors from above, so we're looking at these images here and we're saying how can we apply sine theta and cosine theta to find the orange and green arrows, then we get this situation. We can break apart the velocity vector in blue into its horizontal and vertical components. And in order to find the magnitude or size of these vectors here, the green horizontal component and the orange vertical component, we use these equations. Rearranging these values, vi, vx, and viy, to fit into these two equations for opposite side and adjacent side, we can see that viy, which is the side opposite the angle, is equal to the hypotenuse, vi, times the sine of the angle. The magnitude of the adjacent leg, vx, is equal to the hypotenuse, vi, times the cosine of that angle. And you don't ever have to memorize things like an object fired horizontally has a VIY that's 0. You can always rely on math to tell you the truth about things. And that's part of the reason why I love physics, is because things are true when they're true all the time, not only sometimes. So if you're confused about why an object fired horizontally has a VIY of 0, feel free to plug in the angle of fire. So for something fired horizontally, theta is 0. Sine of 0 is 0. And so VI times sine theta, which tells you VIY, would be 0. Cosine of 0 degrees is 1. And so VI times 1 is just VI. Therefore, Vx equals VI. And the reverse is true for something fired vertically up in the air. Sine of 90 equals 1. And so when you plug in 1 for sine 90, you see VIY equals VI, or all of the velocity that exists in the y direction. Cosine of 90 is 0. So VI times 0 is 0. Therefore, Vx is 0, or another way of saying that is that all of the velocity exists vertically and none of it exists horizontally. You can also solve for the unknown angle theta if you have those two lengths, or if you have two of the three lengths, such as the opposite side and the hypotenuse, or the adjacent side and the hypotenuse, or even the opposite side and the adjacent side. Essentially, what you're doing is finding this ratio of numbers and then taking the inverse function, sine, cosine, or tangent, in order to solve for theta. And those are buttons that would be on your calculator. When we solve a problem, we said that there's a few steps we always start with. The same steps are true for 2 dimensions as 1 dimension. So initially, you should definitely set your 0 and define your coordinate system, meaning one direction is positive and one direction is negative. The first step in solving our complicated 2D problems is to, number 1, draw a picture. So after you've set your coordinate system and picked a 0, you're going to draw a picture. The second step is to resolve any vectors that you see that are at an angle. So if an object is fired at 37 degrees with an initial velocity of 10, the second step, after you've drawn your picture, is to resolve that 10 meter per second vector into its horizontal and vertical components. Once you've broken apart any vectors into their components, your third step is to make your x and y table. When you write out the variables for the x and y table, you should always have delta x, vx, and t in the horizontal direction, and then delta y, viy, and t. And in addition to those three in the vertical direction, we also have vfy and ay. It's really convenient to write or align the t's in your two tables across from each other, so you remember that t is the same in the x as it is in the y. And that's one of those quintessential solving tips, right? Remember we said that there's certain tricks to solving the physics problems. One of them is recognizing that t is the same in the x as it is in the y. Another one, which you've seen from the rocket problems and from the race car problems, is that sometimes the vf from the first part of the motion is the same input as the vi for the second part of the motion. So realizing that at this point here, at the peak of motion, the velocity that the object has right here is simultaneously the final velocity from the first half of motion as it is the initial velocity for the second half of motion. Something else to recognize when projectiles are fired and land at the same location, meaning delta y is 0, is that the shape of the parabola is symmetrical. And what that means for us is that the trajectory, or the time in the air, is split in exactly half. So it takes exactly half of the time for this projectile to reach the peak and exactly half the time for the projectile to fall back down. At this point in the middle, at the peak, whenever we're at our maximum altitude, recall that Vy is 0. And the reason that we don't indicate Viy or Vfy is because it matters which half of the trajectory you're looking at. This point right here is Vfy if you're calling the initial point Vi. This point right here at the peak can be Viy if you're calling this point right here Vf. So there is no automatic assignment to this point. It is neither automatically Viy or Vfy. It just depends on how you set up the problem. And here's an image of your tables. Here's the delta x table. Here's the delta y table. And remember that t is the same. Recall that when you're solving for t, so if you're in a situation where you're solving for t and you don't have Vfy, you don't automatically have to use the quadratic formula. That is one way to do it, and if you're comfortable with the quadratic formula, by all means, please do it that way. But another way to solve a problem when you're looking for t and you don't have Vfy is to do 2 steps. Solve for Vfy first, and then using the value you got for Vfy, use that again to find t. So you can always take a 1-step approach or a 2-step approach. And there's many different ways to set up and solve the same problem, which is why I always say in class there are 14 permutation different ways of solving the physics problems, because every person in class could possibly solve a problem differently. But we would all get the same answer as long as we adhere to the rules of physics and the rules of math.